Howdy class. Here are your lecture videos for sections 3.6 through 3.8. I don't need the contact information slide anymore. You should be able to reference it in the syllabus or eCampus or one of my previous videos. So I'm going to start with some announcements real quick. The labs started this week. I believe you all have lab on Thursdays. Sorry, on Tuesdays. So you should have attended a Zoom meeting today, or if you're watching this on Wednesday, yesterday. I don't know why it says yesterday, sorry. You should set up your Hayden McNeil account this week. Nothing is due before next week, but you should have your account set up because you will start using it very regularly starting next week. The homework assignment that's due tonight is chapter 3.3 or section 3.3 through 3.4. I took off the 3.5 questions as I mentioned in my email, so just 3.3 and 3.4 this time. And it is due at 11:59 p.m. tonight on September 1st, if you're watching this today on Tuesday. Anyway, there will also be a participation question or questions posted shortly after this video. So make sure you do those by tomorrow night on the 2nd at 11:59 p.m. is when it will close. Make sure you do it. I know some of you forgot about this past one, but you'll have participation questions with every lecture video. So just make sure you keep a reminder to do those in, I don't know, your calendar or something. Okay, so this is something that I wanted to get to in our REEF session, our problem session on Monday, but we didn't get to it. So I'm going to talk about it now because a lot of people have been asking about it, and this is a really important concept for you guys to understand. So this is an energy diagram, and there are lots of questions we can ask about this type of energy diagram. For example, you might get a question on how many wavelengths can be emitted based on this energy diagram. All that means is how many energy transitions are there, because the wavelengths, that's for a photon. So how many different wavelengths of photon can be emitted, and every time a photon is emitted, that is because we changed energy levels. We went from an upper energy level to a lower energy level. So how many of those transitions are there? It tells you how many wavelengths can be emitted. So there's one that goes all the way, I'll call this 4, 3, 2, 1. There's one from 4 to 1. There's one from 4 to 2. And there's one from 4 to 3. There's one from 3 to 1 and 3 to 2. And finally, there's one from 2 to 1. So that means there are 6 wavelengths that can be emitted based on this energy diagram. Okay, what's another type of question you might get for this? Another type of question you might get is, what's the transition that emits the shortest wavelength or longest wavelength? And I'm just going to write lambda for our wavelength. So for that kind of question, you have to remember that E is equal to h nu or hc over lambda. Because E is equal to hc over lambda, that means they are inversely proportional. When one goes up, the other goes down. So For example, if you plug in random numbers for a wavelength, if we plug in 100 nanometers and compare it to 1 nanometer, any number over 1 is going to be bigger than that same number over 100. So 1 over 1 is bigger than 1 over 100. So when the number in the denominator gets bigger, the energy gets smaller. So if we want the shortest wavelength, then we want the biggest energy transition. Small wavelength, big energy. So the biggest energy transition is this one right here, 4 to 1. So there's a lot of energy released when we have that transition. And because there's a lot of energy, that corresponds to a tiny wavelength. So big energy, little wavelength. Okay? So those are the kinds of questions you might get for these energy diagrams. And that's good for you to know because it will come up on quizzes and exams. All right, let's go to the new stuff. All right, so we're just going to talk about chapter or section 3.6 for a little bit. There are no homework problems assigned with this section. It is pretty difficult for a general chemistry perspective, so we're not going to ask any questions about it, but it is important to talk about. So since the electron can behave as both a particle and a wave, neither one of those descriptions tells the whole story. So you can't describe an electron only as a particle or only as a wave. There are some things that don't work for the particle definition. There are some things that don't work for the wave definition. For example, Bohr's model only works for the hydrogen atom. It doesn't really work for atoms with more electrons because electrons are really unpredictable. They're really tiny, they move around really fast. So that's where the uncertainty principle comes in. So Heisenberg's uncertainty principle tells us that it is impossible to know both the precise position and velocity of a particle at the quantum scale. You can know one precisely, but you can't know the other one. You can't know them both precisely. And that's because the electron is acting as a particle and a wave at the same time. So how do we write that? So this is the algebraic or the formula definition for the uncertainty principle is that x, so x is our position or location, x is the particle location, and the delta just says that it's a change in location, so you don't know. So what do you know about the change in the location of the particle or electron is often what we're talking about. And delta P, P is the momentum of the particle, but momentum is just equal to mass times velocity, or I guess that should be a U. We like to use our U now. So because momentum is equal to mass times velocity, we can rewrite it as delta x times m delta v, because the mass is not changing. The location and the speed of the electron or the particle can change, but not the mass. So that one doesn't need a delta. So delta x times m delta v is greater than or equal to Planck's constant divided by 4 pi. So basically, Planck's constant divided by 4 pi is a really, really small number. So the certainty in these values is going to be a really small number. So it can't be too small because we're going to know the certainty of one or the other, but not both. So if you have a high certainty of the particle's location, that means you have to have a small certainty of the particle's velocity for this principle, for this formula to still be true. They have to balance each other out and stay bigger than this number. So the change is corresponding to the uncertainty. So even if one of the uncertainties is really small, like you know it really well, then the other one has to be bigger so that it stays above this number. Okay? That's all you need to know about the uncertainty principle, is that it is impossible to know both the precise location and velocity of a particle at the quantum scale. Anywho, what else can we talk about related to quantum mechanics? So Schrodinger's equation relates this wave function, which is represented as a psi. That's a Greek psi. So the square of the wave function is equal to the probability of finding an electron in a given region around the nucleus of an atom. So basically, he came up with this really fancy equation called a wave function to describe the energy of the electron and the region in space where you can find it. So that's what we have with our wave function. Predicts the energy of the electron and the region in space where you can find it. So the wave function doesn't really mean anything to us, but the square of the wave function does. So the square of the wave function is equal to the probability of finding an electron in a given region around the nucleus. So if you look down here, on the left, we've got a graph of the square of the wave function versus the distance from the nucleus. So, like we talked about before, when the electron is really close to the nucleus, that's more favorable because of electrostatic interactions, because electrons are negatively charged and the nucleus is positively charged because it's full of protons. So the electron wants to be close to the nucleus. So that's why this probability distribution that we see here is really high when it's closest to the nucleus. It's most likely or probable that you will find the electron close to the nucleus. The further away you get from the nucleus, going this way, as r increases, the distance from the nucleus increases, the probability drops down to 0. It's very unlikely, or basically never likely, to find the electron at a certain distance away from the nucleus. Too far away, the electron's not likely to be there unless you give it a whole ton of energy. Okay, so that's what we know from the probability or the wave function, the square of the wave function. This is another way to look at it. The probability is shown here as the number of dots, I guess, on this image. And you can see that there's a whole lot of dots. It's really densely populated here, close to the nucleus. If we call the nucleus 0, 0, 0, 0.000. And as you get further and further away from that nucleus, there's less and less dots. So there's less probability of finding the electron there. And the way that we show that is like this. So we draw these things called orbitals, probability functions. We call them, we draw them like this, and they tell us about the electron density of the atom. So the electron density is how likely you are to find the electron in a certain place. The electron density is highest closest to the nucleus, and then gets smaller the further away you get from the nucleus until it drops off to 0, where there's nothing left out here. So we don't draw that on our orbital because the probability is basically 0 that far away from the nucleus. So there's several different ways to represent this probability of finding an electron. We're going to focus mostly on this representation that looks like a sphere. You'll see other types of shapes in a few slides, and that's what we're going to focus on, these orbitals, these orbital representations of the probability of finding an electron in a given region. So that's as much as we're going to talk about for quantum mechanics. Quantum mechanics is really hard. You can take grad school classes on it, so you can still be working on your PhD and taking a class on quantum mechanics. It's that hard. So that is pretty much all you need to know for now. And here's a cute little picture that I found of Schrodinger's cat. So I don't know if you've heard of it before, but Schrodinger came up with this fun theory or principle that if you put a cat in a box and you close the box, you don't know whether the cat is alive or dead inside of the box until you open the box. So until you open the box, the cat is technically dead and alive because you don't know the answer. You can't be certain about whether it's alive or dead. So it's both dead and alive. And this is a wanted poster for the Schrodinger's cat. All right, let's keep going. Let's talk about something new.